Good evening, everyone. So today we'll be doing triple integrals and spherical coordinates. This coordinate system is great when you're dealing with surfaces with spheres or cones. Okay, so if you really had a surface that was a cylinder, it's better to do things back in cylindrical coordinates. As we saw in some of the problems we did previously, we dealt with this, something combined with the cylinder. But we're doing triple integrals and spherical coordinates. This can be beneficial, make the problem easier to work if it's dealing with a surface that's a sphere, or maybe a cone, or both a cone and a sphere. So two things we're going to have to do is develop the volume element for doing things in spherical coordinates. I mean, remember with polar coordinates, what was automatic? That R? We're going to have to go get that thing going, right? Make sure we get that. So we're going to have to do that with spherical coordinates. So can you help me draw a nice picture here? I'm going to add some symbols to go spherical coordinates. This is what we had in cylindrical coordinates. You had a theta, and when it looks distorted because it's three-dimensional, but there's a 90-degree angle right there, and then there's another 90-degree angle here, okay? But can't we call this distance x from here to here? Mm-hmm. So I'll do that. And the distance from here to here, y. All right, I'll do that. And then we call this distance right in there, from there out to here, r. Go the other way. So I just want to make sure everyone gets that triangle down. That's x, that's y, that's r. See the right triangle, Pythagorean theorem. And that's really polar coordinates, right? With the x and the y and the r. Then in cylindrical coordinates, we said, oh, you can have a variable z. And you can go up or down a distance z, and that allowed us to do cylindrical coordinates. Now we're going to talk about spherical coordinates. All right. So spherical coordinates, we're going to talk about how you take a point just right from that origin and then go straight out. So would you draw a line right here? And we're going to label this. We're going to call this distance rho. I know it's the same Greek letter they used when we did what? Density? But it's totally different from that density. It's just a variable we're going to use. It represents the distance from the origin, straight out in space, in three-dimensional space. And it's the Greek letter rho. So do you all notice we have another right triangle in here? Mm-hmm. And the right triangle has a length of r, it's got a length of z, those are the legs, but the hypotenuse is this Greek letter rho. So that's one of the variables in spherical coordinates. It's just the distance from the origin out in space. Kind of neat. There's another angle that we got going on, different from theta. So we're going to use another Greek letter, we're going to use phi. I need you to know where phi is. Phi is the angle formed from the positive z-axis outward. So right in here, I'm going to put a phi. Phi looks like that. Here's phi. Yeah. So here's phi. Phi comes out from the positive x-axis. I'll just draw an arrow like that. Phi is formed such that, it's adjacent to the positive z-axis and just comes outward. Which, if you can tell, that's why it makes it really kind of easy with cones. Because you just bend out like this from the positive z-axis all the way around, giving that cone formation. And I want you to draw phi somewhere else. You remember in geometry class when they said alternate interior angles are congruent? Do you remember that? So if that's phi, guess what I can call that angle? I can also call that phi. You notice this is parallel to the z-axis? Uh-huh. So in your drawing there, would you also note that this can be called phi? It would be equivalent to phi. Right there, we can call that phi as well. Someone got it? This is going to be spherical coordinates. What are the three variables? Rho, theta,
phi,
and you got phi. Those are the three variables. What were they in cylindrical? In cylindrical, it was r, theta, and just a z, right? Or you're using the same theta as before, but you also have a rho and you got a phi. Some textbooks do this in different order. They put the phi before the theta. I'm going to stay consistent with your textbook, and I noticed in your textbook, everyone, I'm looking at page 1033. This is the order they use. All right, but I do want to point. You look at another text, they might put the phi before the theta because they're just different angles. Where's phi being formed? From the positive z-axis. So on that note, everyone, I'll use markers to help us see this. phi will never go higher than pi. Think about it. Let me just get out of here. There's the positive z-axis, right? That red marker. Well, if I form an angle from here, okay, if I get down to the xy plane, I only went 90 degrees, right? But the furthest I can go for anything, like forming a sphere or a cone, is straight down. And you notice that's the angle pi? So the limits for phi is 0 to pi. Phi only goes from that phi angle. Or excuse me, phi will only go from pi to 0, never higher. That's its extreme. Because you just pull it all the way down. You might say, well, what about going back up? Well, we're talking about from the z-axis in all directions. So you got theta, here's theta, right? Theta's down there in the xy plane. You got phi coming from here, and then you have this distance rho we're talking about. Cool. So I don't know. Let's see, where would this point be? How about 3? Let's say theta is pi over 2. And let's say rho is pi over 2. Can you help me figure out where that point would be? If that's rho, that's theta, and that's phi. Can we just get a sense of where that point would be? Well, it's got to be how far from the origin? 3. Distance of 3 from the origin. Theta rotated it, what, pi over 2. So where's theta is down in the xy plane. So it rotated 90 degrees from here, putting it on which axis? The y-axis. And then how far did it come down? It bent down 90 degrees, which will put it right in the xy plane. So it would look something like this. Let's just label this. There's your y-axis. There's your x-axis. There's your z-axis. This point would be right here. Do you notice that? Because it went a distance of 3, it rotated what? 90 degrees down from the positive z-axis, but it rotated pi over 2 this way. Cool. I just want to give you a simple point, because if I give you another bizarre point like pi over 4 or pi over 6, it might look out here or something, right? Where's this point? 3, 0, pi over 2. Where would that be? So 3 from the origin, rotated 0 degrees for theta, sitting right on the x-axis, but it came down.
5 or 2.
Yep, so this would be over here. Just to give you some easy points of where you can recognize where they would be located. Cool. Nice. Okay.
So
Well,
theta will always be between x and y, right? The angle.
That's right.
Okay.
It will. It always will be. And one thing we got to do now, we got to talk about doing triple integrals and spherical coordinates. Let's talk about the volume element. Now with polar coordinates and double integrals, the polar coordinates, the area element was RD theta. Right? It was RD theta. Now we have rho d phi, RD theta, in this d rho. Do you notice that? Well, then we got to put something for this. We got to put, so excuse me, these are fine, but which variable in here is not one of these 3? So we got to substitute it, and then we'll make up the volume element. Kind of like that RD theta we had for polar. Which variable? Do you all see it? With the R. So we're going to have to put something in place of that. So let's use this. You'll notice it comes down to 2 right triangles here. You got this what? You got this one triangle that is, I'll draw it again right here. There's like an X, there's a Y, and there's a R, right? And there's theta. What's the other right triangle? I'll put it right next to it. What's the other important right triangle that we have?
R rho z.
You got it. So I'm going to put it right here. And when it's in this image, but I just wanted to draw it again. You got rho, you got z, and you got an R here. And where's phi? Be careful. Is phi here or here?
Phi is
Look carefully in that image.
between
That
rho
right
and z.
triangle, phi's up here, isn't it? Does everyone see that? Be very careful. I think it's easy. This comes down to, it boils down to 2 right triangles in there. And there's a phi right there. Because it's equal to that angle, which is outside that right triangle. Cool. So, what were the equations back in polar coordinates? Well, I had x equal to r cosine theta, and what was y equal to?
Sine theta.
Or sine theta. Well, I'll leave that there. So we're going to need something new for spherical coordinates. It's not going to be hard. It's coming from this triangle here. Everyone, can you tell me the relationship between r and rho? So I can substitute something for that r. It looks like r and rho, you know, SOHCAHTOA, opposite of phi, and you got this rho. What's sine of phi there? In that right triangle. Opposite over hypotenuse?
Yep.
So what is r equal to? And I'll leave it on the board, all class.
Rho sine phi.
That's what r equals to in spherical coordinates. If you're like, oh, I gotta memorize it. Sometimes it's not really memorization, it's just drawing a picture and just looking at it. But I'm gonna leave it up all class. R is always equal to rho sine of phi, as you can tell in this right triangle. So, this is all I need to make spherical coordinates. That was polar? That was polar, right? Then what's spherical? What is spherical? X equals, I can just replace this r with a what? A rho sine phi. It's going to look long, but there it is. That's what x equals in spherical coordinates. Does everyone notice? I just substituted the rho sine phi for the r. What will y equal? I know they look long. Welcome to spherical coordinates. But this actually makes problems easier. Can you believe that? We wouldn't, I know. People are shaking their heads like, what the heck? Makes some problems that deal with spheres and cones easier. What does y equal to? Rho sine phi sine of. Now we need one more variable. What's z? That's going to be easy. Just go back and look at that triangle.
Z goes to.
You'll notice it's something with cosine in it. Because z's on the adjacent side of phi. So what's the cosine of phi there?
Z over
Cosine of phi is z
over rho.
over rho. So guess what z is?
Cosine.
Just rho. It's short. It's not long like the x and the y. There you go. And those are the three conversions. But you'll notice something. It's like, oh, I got to memorize this. More than memorization, it's conceptual understanding. Seeing what these triangles are, and you can build it yourself. All I did was take polar. All I did was take polar and replace the r's with the rho sine phi. That's all. But I had to look at this triangle though again to see what would the relationship between the z and the rho be in terms of phi. So z is equal to rho cosine phi. Cool. There they are. Leave them up all class. I can move this over and just put them right here because they're long. X is rho sine phi cos theta. Y is rho sine phi sine theta. And lastly, z is rho cosine phi. Leave them up all class. Everyone go with that? Nice. We should add one more then. We should definitely add one more. I'll write them right there. Put that down so we can see it. Pythagorean theorem. R squared plus z squared equals.
Rho squared.
Everyone agree? What was r squared back in polar? X squared plus y squared. So guess what we got now? X squared plus y squared plus z squared is equal to rho squared. Does that look familiar? Isn't that the equation of a sphere on the first day of class in section 12.1? How cool is that? Section 15.9, that's the equation of a sphere. X squared, except we use the letter r, remember? We use the letter r. Well, from now on, we'll use a phi. Or excuse me, we'll use the Greek letter rho. So it looks like a p. That's the equation of a sphere. X squared plus y squared plus z squared must equal rho squared. So back to this. So let's just write this out. What will triple integral, you know, a function of x, y, and z, you know, in Cartesian, what will this be equal to? Okay. Well, it'll be, I think I got enough room, because these are long, aren't they? F of rho sine phi cos theta, rho sine phi sine theta, rho cosine phi. And I'm about to put down d rho, d phi, d theta. But there's other stuff.
Or
And I need you to focus in on this, everyone. Right there, this three-dimensional object to figure out what's the volume element for spherical coordinates. It's right here. It's got a d rho, it's got a rho times d phi, that would be this side. See this three-dimensional box that I made there? I know, it's almost like just a speck, it'd be infinitely small. D rho meaning really, really small part of rho. This is just rho times an angle phi, but I'm thinking like infinitely small, like change in phi, d phi. But then this part, that was r d theta. What can I substitute for r again? And I'll put it right now. What can I put in place of the r? Rho sine phi. That's that little dimension there. So see it's like a little three-dimensional object there. It's got this side, and this side. Well, d rho, rho d phi, but the r d theta is now rho sine phi d theta. So when you put boxes on three of these, we're going to put it as a volume element. It would be this, and all of that. And that's going to be my volume element, the product. Length times width times height. How many rows you got in there though? You got two. It's a rho squared. Everyone see you got a rho times a rho making it what? Rho squared, and then there's a sine of phi, d rho, d phi, d theta. D rho, d phi, and d theta. I got all three.